This is just an exercise. Derive the electric field intensity of an infinite line charge and show that the electric field intensity due to infinite line charge and charge density rho L is E equal to rho L divided by 2 pi epsilon naught R in direction of R. This one we already discussed before. Now you have to derive infinite line charge. Okay, the same thing. This is how can we find the expression of E, okay, for a line charge placed on the z-axis. Like what I show you before, that is the conclusion from the analysis. But this is a basically this figure shows how the analysis is done. It's quite long. Let's see. Okay, this is how you do it. We have the general expressions for Coulomb's law. This is the first part, and then assumes that z prime represent any point along the line charge and z represent any point along the z-axis. So we can define R, the vector equal to R in direction of R minus z prime minus z in direction of z. So what is the meaning of this? We have to refer to the figure. So basically z prime is here. Let's say you take a sample charge here. This is your sample charge. So we put the sample charge, the one of the point here, to be z prime. The location is at z prime, and z is basically normal to the point P. Okay, normal. That is, so we have z prime minus z, these locations, and this vector R. How to define vector R is basically it's going down and then it's going to the other actions. So this it become this form. Next, you have to integrate, okay, into dz prime. Why dz prime? Because the z prime is our variable. Okay, because the z prime is something here, and the location is anywhere on the line chart, but your limit of your line chart is from A to B. This is where the integration should be made. So you have the rho L dz prime, and the integration of dz prime from A to B, because that is the length of our chart system. Okay, this one is divided by 4 5 epsilon naught r square plus z prime minus z square 3 over 2 r in direction of r minus z, z prime minus z in direction of z. And then you can separate into two components, which is component, okay, r, and then component z. And then this is a integration identity that will be given to you. Okay, you can see this form will become this, and this form become this. So you have to compare. Well, from this identity, so our solution of this integration become this form. We have the r cap divided by magnitude r, and then we have z. And then this is where we define the alpha 1, alpha 2 depend on the figure, and it can be simplified into this form. Okay, this is the things. And this form, okay, we can define as a triangle. Okay, the triangle, the trigonometric form. When you see this is triangle. We have two triangle. Okay, we define as a alpha 1 and alpha 2 refer to the our R. Okay, this is the normal line, okay, from our chart system to this point. So our reference, okay, the reference line. So we have alpha 1 and alpha 2. Alpha 1 from A and alpha 2 from B. Right, we have two definitions there. So we have to define alpha 1 and alpha 2 using trigonometry. Theorem Pythagoras, very simple. So you have to compare, and then this form b minus z and then a minus z, and then 1 over r square plus b minus z square half, and this is become this form. We have sin alpha 2 plus sin alpha 1 plus cos alpha 2 minus cos alpha 1, so on. So please prove this. Okay, you have to do it yourself and prove that the final expression become this form. Please practice. And this also, like I mentioned earlier, what happened if our line charts become very long and extended towards infinity. So the alpha 1 and alpha 2 approaching 90 degrees. So this part will become 0, this part become 2. Okay, that's why we can simplify into this form. So this is your homework. Please do it before I give you the solutions. Okay, we have only, I think, 4 questions here. Please do it as your homework. So we finish chapter 2. If there any question, you can ask me later on. Thank you, and see you again.